Hi, in this video I will be demonstrating how to set up your STM32CubeIDE workspace for embedded ARM development, especially for STM microcontrollers. So after downloading your CubeIDE software, navigate to your folder and unzip the downloaded application. Double click to start this. It may ask for some permission. I'll allow it and click on next. I agree, and then I'll be selecting the destination folder. The destination folder is the place where your application will be installing. In my case, this is my root directory. It looks fine to me, so I'll click on next. I'll select the components. I want the hardware drivers as well as the core to be installed. So I'll click on next. It will take some time depending upon your computer speed, and it may ask you for a few other permissions such as for installation of the drivers. I want to install the drivers because I want the debugger software and the hardware to be working with this. So as this is installing, I'll be waiting for this. It may take some time for you to install. For me, it took about 10 minutes. You might need to be connected to the internet in order to install this. So while this is happening, I'll be I'll be switching to my other workspace. Once this is done, I'll be making a shortcut on my desktop. Alright, so this is the CubeIDE software. So on your first launch, it may ask you for a few permissions and it might take a small time to launch as well. So this is now first asking me to make a directory or my workspace. This is where the default place will be for the storage of my project files. I want to change this to my root directory. In some instances, I have seen people suffering with debugging if they choose a user directory because of absence of privileges of your debugger to access that directory. So the best course of action would be to make it on your root directory. So I'll make a new workspace. I'll call it ARM workspace and I'll add a new folder inside it, which I will call CubeIDE workspace. I'll select this folder and I click on use this as my default and do not ask again. This will make your default workspace and I'll click on launch now. So the CubeIDE is based on the Eclipse IDE, and Eclipse being an open source tool is based on Java. So your CubeIDE is an offshoot of the SW for STM32 or the SW STM32 software. You might see that the interface is very much similar to that as well as the debug procedure. I do not want to collect any data and but I want to give it internet access. So I'll give it allow access to my local network. I'll click on no. Doesn't. Alright, so to get started, I would want to click on start a new project. I'll select my part from here. So you have two options, which is if you have a development board, in which the most popular one is the nuclear board. You can search for your particular nuclear board, or you could also go for searching for your own microcontroller chip. So I happen to have a nuclear F401RE, and this is listed in the list of boards that it supports. So I may select that and click next from here, or if you want to select an MCU, in my case I'm using an STM32F103C8 MCU. You just select that and it will show up on your right side. So once you click this, you might get options for other documentations and resources. I would want to use the programmer's manual for this. So if I click on this, it will open it in my browser and this will redirect to my programmer's manual, which is on the ST website. If I want, I can save this on my local PC. I would also want to use the datasheet for this. So the programmer manual is primarily necessary for locating your registers, and your datasheet will tell you about the overall electrical and the physical characteristics of your microcontroller. I will save both of these. It's a good idea to save this beforehand in case you're not connected to the internet quite often. So once I have saved this, I'll close this and I'll return to my ID. I click on next. I want to give project name. Now I want to save this and make this project in my default workspace. So I'll click on default. In case you want to save it elsewhere, you would want to uncheck on the use default location and change the name of your location to or browse it in your file space as desired. I want to do this in my default location, so I'll click on finish or next over here. I'll just confirm the firmware directory. The firmware version seems to be the most recent one. You have options for copying only the necessary file. This is useful if you are redeveloping a project and you just want to copy the necessary files, or if you are making it from a pre-existing core such as the one generated by CubeMX. So once you do this, on the first time you are working on a particular chip, it will download the firmware packages from your internet, and your firmware packages will be stored in a folder that was the place generally on a computer. So I'll be showing you where this firmware packages goes. In order to see where does it go, you can check on the project and generate code to see the location for firmware packages, or you can click on firmware updater and it will show you that your firmware installation repository is in fact in your user folder. So if I go to this place, I will find the location where my downloaded firmware packages are located. All of this is done by STM32CubeIDE. If you want to change the default one, you can just click on browse and change it. I'll just close this. If I made changes, I'll be clicking on apply. So I'll, this says okay. So I had cancelled my code generation, and this might also be issue if you are not connected to the internet or have a poor connection. So what you can do is just locate to your firmware directory and download the firmware separately and place it over there, and your ST will directly recognize this. So once I click on generate code, in case my files or my project does not have the required set of files, it will directly download it from the internet. So let's wait for this till it completes. In case you have a partial download, it may continue from there, or if you have a broken download firmware, then it will download the whole thing. So just to show you where this goes, in my system it happens to be in my user folder. So the user folder has the folder called STM32CubeIDE, not the one which I just showed. So if you go and look, you might find this. So in this case, it happens to be the STM32Cube, and you have the repository over there. So this is the firmware, STM32Cube firmware underscore version 1.8. So you can find the same firmware on the website. So if I go to the website of ST Microelectronics and I look for the firmware for my particular chip, I can find it as well. So just go to the website ST Microelectronics. So on the ST website, I will be looking for my chip, which is STM32F103C8. I'll click on it and this will open the device page for that particular IC. So inside this, I will be looking for tools and software, and your data will be present in that. So once I click on tools and software, it shows me all the lists of software that comes with this. We want to find the particular microcontroller firmware. So I'll click on this STM32Cube F1, and this is perhaps the package that we want. So you have a patch for this, which is version 1.8.3, sorry, 1.0.3, and you have your main firmware, which is 1.0.0. So since we saw two sets of downloads, the first one was your main download and the second one was your firmware patch. Just to compare this on my folder, perhaps I happen to have both 1.0.0 and 1.0.3 on my system. The main firmware is about 100 megabytes and the supplementary or the patch is about 11 megabytes. So in case you are unable to download this using CubeIDE, you can download it from your product page online and you can just paste it within the folder which has your repositories. So next, after doing this opens the CubeMX perspective. Now, perspective is basically a set of tools within a window, and this term is for Eclipse. And in my case, I'm in the MX perspective. In fact, I'm not in the MX perspective, I'm in the coding perspective. If I click on the tools, the MX perspective, it will take me to the CubeMX window. So CubeMX is a standalone software in itself, but this IDE has this integrated within itself. So CubeMX is a tool which allows you to uh, configure your IC and the pins on the IC without making any kind of code, or you don't have to write code in order to set pins. If you want to set it as an output or an input, or maybe use some communication protocol, you can do that all by just graphical user interface. So what this MX perspective does is basically make a set of files or the drivers for your IC and it links it to your main file. So this is my chip F103C86, and if I click on the drivers, I see the HAL drivers. HAL stands for Hardware Abstraction Layer, and this layer of abstraction is provided by ST Microelectronics. Abstraction is basically making your life simpler. It, it separates your underlying register maps and the register settings from your main application code. So you just have to write your logic inside it and just use the drivers or the APIs which are given by the hardware abstraction layer. So you see all these that are present in your HAL drivers. You have your DMA, your flash, your GPIO, and your RCC. So in case I want to add additional functionality such as the SPI, once I click on SPI from my left side, it enables all the three pins for which are supposed to be for the SPI1 or the SPI1 set of serial programming interface pins. And as you change the pin configuration or the mode, you will see more or less number of pins that are turned green on your GUI on the right side. If you want to add a NCC or NSS signal, if you enable this, it will utilize one more pin, and the pin which has been set by default for NSS purpose will be turned on. You can change the parameters in these device configuration or the port configuration settings. You can set your rate of SPI, you can set it as high or low, or you can use the protocol standard that you want, and so on and so forth. So once I set this, if I click on generate code, on my left hand side, you will see within your HAL folder, your HAL driver folder, the SPI drivers and the APIs for that, your source code for that will be updated. You can see that spi.h the header file and spi.c the source code files have come up. And if you open this, you will find that it has all the drivers that are supposed to be used for the SPI functionality. So you then just only need to use the functions that are within this. You just import your SPI header file into your directory and you use the functions. You have the callback functions, you have the transmission and reception functions, and so on and so forth. So this is a very convenient way of using the SPI libraries given by ST Microelectronics. It's very well documented. You can just import the directory of SPI within your code and you can use the different functions that are given within this file. It gives a comprehensive list of functions in the beginning and then all the different functions that are there, and your macro definition for the functions are also given. So you can just explore this if you wish to. All right. So we are mainly interested in our main.c function. This is where the user code goes in. You might have additional files that are linked to your main, but the entry point in the application for your code is the main.c. So in my particular example that I will demonstrating today, I do not need the SPI functionality, but I do need the GPIO functionality. And we are going to do the classic blink example. I'm going to set this pin as an output. And once I do that, I'll be setting this as an output over here. And I'll go to GPIO and I'll be setting that as an output high. So right now it's an output low by default, which means it's an invert logic. So if you send an high on this, you'll get a low at an output. But if you want to set it as an output high or your normal conventional logic, in that case, you can change that to output level 2 high. All right. So once you do that, it shows a tick on your modified. So what is this is basically doing is basically changing the parameters within your code. So once you are done with this and once you click on save the or run the project, you would see all these changes that reflect in your main.c file, which has the initialization code for your particular uh, driver that you are using. I'm using the term driver, which is in conjunction with the term API. So driver and APIs are basically the same concept when it comes to programming in C on microcontrollers and embedded systems. So if I scroll down, I will see all my initialization code that is already placed for me over here. And if I go down, you can see the SPI initialization that has been set. If you have selected a UART, you will see the UART initialization. And over here, I see my GPIO initialization as well. So within the GPIO initialization, you can see the different things that need to be initialized. You have the pin, the mode, the pull, and the speed. MX stands for the code CubeMX that we are using. And MX is basically the software which is developed by ST to do this in a GPIO or a GUI way. So if you click on this, you'll see the macro expansion for the different functions and the different macros that's used here. You see the function definition within this. I want to set it as a high pin, and that was changed by setting the right pin to pin set, and that sets a high on my pins on the output. So if I see this in conjunction with my MX software, you will be seeing that as I make changes over there, it will similarly reflect over here as well. So this is my GPIOC and it has the pin 13. And on my MX software as well, if I go to the MX perspective and if I make changes over there, it will be reflected in a similar way here. All right. So whenever you are making code, just ensure that you always start and end your code within the begin and the code end brackets so that it stays there. More on that later. So I'll go back to my MX perspective, and over here I will be showing you what does the changes made on your MX software reflect to in real time on your chip or on your code. So over here you have the pull up sets to no pull and the output signal is set to low. So it asks me if I want to switch to my C perspective as I click on my C file, but I want to be in my MX perspective. So if I set the GPIO output level to low or high or the speed to medium or low or high, you can see as I set it to output level to low, and if I save this, the output level on this will indeed be changed to low. Similarly, if I change it to pull up type and the speed to be high, you can see all these parameters change as soon as I update my code or generate my code for this. So once I click on generate code, you can see these parameters change. So you manually can also change this instead of going into the MX perspective. But since this is not within the scope of user code, once you do this again on the MX, your previous configuration that have been done manually will be overwritten. So it is always best to use the MX software only if you are using MX software at all, or just use the configuration file that is generated if you want to do changes manually. So we as a user will be generating and writing our code within this main function. You can have your sub functions before this, and always remember, whenever you are writing code, you should write it within the begin and the end blocks, which are given in comments. This is because MX basically overwrites the file, the main files and all the other files, and if it finds that the code is outside the begin and the end block, it is not going to include that in the new or the overwritten file. So just as an example, I will be including a general function which is a standard IO function for C program. And so if I click on include stdio.h, it will import that into the project. And I'll be doing it twice, once within this begin and the end block, and second time I'll be doing it outside this. So once I do this, I will be saving my file with a control S so that it's saved over here. And I'll be then moving on to my MX perspective, where I'll be making some changes just to demonstrate that MX file indeed overwrites your code and only retains the stuff which is within your begin and the end block. So I'll be switching to my MX perspective. All right. So here I will be making some changes. Maybe I want to set this another pin as an output pin, and I'll be making some modifications. That's it. Okay, all right. So I will be clicking on Control S. Another way of updating your code is by simply saving the perspective. And so once you do that, it will be making changes. And perhaps once this is done, you will find that the code which was outside the begin and end block within the line 27 over here has indeed vanished. So always ensure that whenever you are writing code within this software, it is always within the begin and the end block. It can be within any begin or end block as soon as, until your logic is correct. But if it is outside a begin, or maybe before an end, before a begin or after an end, it will vanish once you update your code using the MX software. Alright, so I'll be writing a simple Blink program, and then this is beyond Blink. We will be going a bit further than basic Blink program. So I'll be setting using the drivers, and drivers are your APIs. So as soon as I click on HAL underscore GPIO and click on controls and underscore, control and spacebar, it will give me a list of options which I can use. So I am using the GPIOC, and you can see all these macros that come down to help you to select the correct one. Similarly, I'll be using the delay function, and this function is given by the HAL drivers. So if I click on HAL underscore delay and open and close brackets, and I set a delay of 100 milliseconds, it will be creating a delay function. And that's it. This is the initial Blink program for you, if you will. This is basically using the toggle pin function, which means on every iteration, it is going to change the state of the register which holds the value of the output state of the pin. So if it starts with a 1, it will then on the next iteration, it will set it to 0. And then again on the next iteration, it will set it to 1, and so on and so forth. And since it's a while loop, an infinite while loop, we will keep doing this until you terminate the code. All right, so I compile this using the build option. You see the hammer icon upstairs. That is what you're going to use, and this gives you a very good visual description of what kind of resources you are using on your microcontroller. And since microcontrollers and microprocessors are always resource hungry and resource limited, in fact, so you would want to ensure that you never fill up the flash and the RAM, and your code will keep running properly. So here it shows me that my RAM utilization is about 1.6 kilobytes right out of the box, and then my flash is also on a similar scale, and I'm good to go at over here. So what I'm doing now is I'm changing the view of my perspective. If you want to move around stuff, you can do that, and if you want to keep a same perspective, you can just switch back to default. So on the right side, it shows you all the helping functions and the functions that are included within this. And on the left side, you see your project explorer. This is your name of the project, and these are all the folders and the files that are included on this. The driver folder, you can just, if you want to see where this is on your computer, you can click on show in and go to your file explorer, and this will show you it is perhaps in the workspace that you created. You see all these files. Your main code is in your core, and your debug consists of the debug data that is made using the build command. So on a microcontroller, the binary file or the bin file is the one that is going to be written on the flash in order to run it, and the ELF file that's there is for the debugging. So if you are using a debugger like a ST link debugger, you can use the ELF file for doing the debug session. All right. So here I'm just checking my RAM and my flash usage. Looks good to me. And I can also see the memory locations within my microcontroller. You see the different memory regions that have been mapped out over here. You have the start and the end address and the utilization address. All right. Looks good to me. I click on Control S. So now at this point, you can go to debug and click on debug and start the debugging session and make the changes in the debug parameters. But since this is beyond Blink, we would want to go beyond the main basic Blink program. So I will be making a small Morse code program. This basically sends the letters S, O, and S, or dot, dash, and dot. And so so I'll be clicking on my while loop, and I'll be typing my Blink code. In fact, a beyond Blink code. So this basically is going to change the state of the dots and dashes, and dots and dashes are going to be separated by a small delay. So I'll be just using the same, I'll be using the right pin command and the function from here. And if I click on control space, it will give me the list of all the different uh, macros that I can use within the function. And once you're writing the function, it will also give you all the different functions that you can utilize. So I'll make the code so in such a way. Mm. All right, so my code is ready now. I can make a few changes in the delay size, and I can add a few more delay functions, and so my code is ready for the Morse code. Basically, the size of your high and low are determined by the set and the reset commands, and each of these are separated, or each of the dots and the dashes are separated by a 200 millisecond delay, and the duration of your uh, pulse, which is the time on which your LED will be on, will basically tell you the size of the each particular pulse. So I have the dots which are sent to 100 milliseconds, and my dashes are sent to 500 milliseconds. So that is how I can tell if it's a dot or a dash. All right, looks good to me. I will be saving the code over here, and so this is basically how you make your first project. In the next session, I'll be teaching you how to do a debug session on hardware if you happen to have a hardware. So just a quick one on perspective. You can save your current look or the look of the screen to as a perspective. You can override the current perspective, and I'll click on yes here. So what happens is if you do this and if you happen to change this accidentally or intentionally, and after a while it doesn't look good to you, you can just switch back to your previous perspective. So click on reset perspective, and it will ask you for a confirmation, and then I'll click on yes. You see my saved perspective is now there in the memory of. Thanks a lot for watching this video.